Well, welcome back, guys. Hopefully, this will be a short but sweet podcast to kind of go over Chapter 6. A lot of Chapter 6 is review, talking about electron configurations, and we'll get to that in a little bit. Nature of matter and some quantum mechanics. So, there's some new things here. Some of this is going to be review from physics, or maybe it's brand new for you. But regardless, let's just kind of jump right in and get this thing done. So, light travels as a wave, so that's one of the big things you need to know. And when we talk about light, another way of saying that is radiant energy. Remember that there's different parts of the wave, like up here we have the crest, and down here is our trough. Although I've heard some physics teachers say tro, I don't know at this school. But anyway, when you talk about wavelength, especially when we're talking about light, really we're going to be looking at the different colors that go into light. So when you look at white light, it is made up of all kinds of different colors. And the symbol for wavelength, and it's this really fancy letter that kind of looks like this. I'm not very good at drawing it, but there you go. The other thing that we're going to look at is frequency. And frequency is a number of wavelengths that pass by any given point in a second. The symbol that they use for frequency is kind of a weird little V thing. So it's not a V like velocity, it's sort of a stylized V, and I'm not very good at drawing it, but you can see it in your book. Another kind of interesting thing to know about waves is when you talk about amplitude. And so amplitude is going to be, this height. And if you think of when you look at your favorite radio station and whatever its station is, that gives you an idea of its frequency. Now in physics you use the unit of hertz to talk about frequency. Well, really we don't use hertz. We have no way to kind of use that unit. What we do need to be able to use is seconds. Because if you think about velocity, and specifically the velocity of light, you talk about the speed of light. Well, the speed of light is c, and that is a constant. It is 3.0 times 10 to the 8th meters per second. So now you can kind of see a relationship between a couple of the different units. Velocity, speed of light, meters per second, frequency, 1/second. Wavelength, we typically talk about wavelength in terms of nanometers, so we might have to make a little adjustment there. Where does the amplitude kind of come in? Well, back to the radio station idea. If you know what radio station you listen to and they give you their call sign, 93.3 or whatever, that is in megahertz. Well, translate that into hertz, which we kind of did in a lab. And then you can put that and figure out what its wavelength is. So frequency and wavelength are kind of related. But if you've ever considered where does amplitude fit in there, well, amplitude, as I said, is this distance right here. You can change the amplitude simply just by turning up the volume, changing the volume of your music. Equations that we need to know are right here, where you've got the speed of light. How is the speed of light related to F, frequency, which is what physics uses? Sadly, your chemistry book is going to use this little v, so really you're going to see the speed of light as more of this type of equation, where you've got that little, I think it's called lambda, not up on my Greek letters, times the frequency. Electromagnetic spectrum. So where is the visible light? Out of all of the waves out there, here's visible light. What we can actually experience is just a tiny, tiny little piece of it. And if you look at white light through a prism, you get all these really, really pretty colors. But the key thing to know about the electromagnetic spectrum is when you get on this end, you have high amounts of energy. Gamma rays, X-rays, this is why you got to wear the little lead shield when you're getting X-rays on various parts. UV, there's all kinds of bugs that use UV. And then we've got the stuff that we can see. IR, infrared, all kinds of applications for that. But on the other end of the spectrum, we have low energy. So we can kind of relate energy and frequency and wavelength. So notice the relationship between how the wavelength increases and how the energy then decreases. So when you can see red light, you're looking at very low energy wavelengths of light. On this end where you got the blue, the purple, it's kind of hard for our eyes to see because it's got such a higher energy level to that. Frequency increases as you go this way, wavelength increases as you head that way. So how does this fit into matter? So that's a little bit about light, but how does matter behave? Well, matter behaves like a particle. And this is a little picture of a photon, which is just a packet of light, and it's kind of showing how a photon travels like a wave. So that's one of the things with this chapter. It gets into a lot of what we call wave-particle duality, and I'm kind of jumping ahead of myself. Because this lovely scientist, Max Planck, and there's his dates of existence, came up with this equation where E is energy, H is what is called Planck's constant. So H is going to be a constant. I'll write that out there. H is called Planck's constant. And of course that V, that is our frequency. So we're kind of relating our frequency and then how much energy we have there. Constant. Let me finish writing that piece. Energy is quantized. What does this mean? Well, quantized just means it comes in very specific amounts, and we call those very specific amounts quanta, would be the plural, or quantum, if you're thinking about just the individual. So how does light and energy fit together? Well, light travels as a wave, as we've already said, but we've also kind of seen that light can travel as a particle. And this gets at the wave-particle duality. You'll see that in some textbooks. Sort of a strange phenomenon that something can be traveling like a wave, so think like a slinky, but also as a particle, as an individual idea. So imagine if we've got light as a stream of photons. This would be sort of more of the particle, where it's just kind of going blip, blip, blip. But it's also kind of traveling on a wave. So kind of the best way that I can think to explain this is just by kind of putting the two pieces together. Oh, by the way, a particle of light is called a photon. I've already sort of mentioned that a few times. Photons can be emitted or absorbed. And so that's something important when we start looking at the electromagnetic spectrum. Why this can get a little bit tricky is because we're asking with our three-dimensional brains to visualize something that's in the fourth dimension. So it's kind of hard to come up with a visual representation of what this is. So this is kind of out there stuff. This is not in your notes packet, but we need to kind of add this in to see what sort of calculations or where do we fit all this energy and Planck's constant and sort of thing. So take a moment, pause, and you might want to write this question down wherever you got some space. Okay, let me back up just a second here. So the equation that we're going to use for this particular problem, the frequency energy of a single photon, is we're going to take that one where we've got Max Planck's calculation, but we can substitute in that, because here's our V, this is frequency. What do we know about frequency? Well, we've got something about wavelength, so what's our relationship between frequency and wavelength? Well, we know that the relationship between frequency and wavelength is the speed of light. So if I take, let's start over here, the speed of light is equal to the wavelength times the frequency. So if I need to know what my frequency is, let's put in a V instead of the F that it says on there. I know the physics people are twitching, but that's okay. So speed of light is equal to wavelength times the frequency. Let's rearrange our equation here so we get the speed of light divided by the wavelength, and that's going to get our frequency. So now we're ready to go. What is the frequency energy of a single photon, energy of a mole of photons, light having a wavelength of 555 nanometers? So let's start by using our frequency equation and the speed of light and the wavelength to figure out what that frequency is. So let's take our speed of light, 3.00, which is times 10 to the 8th meters per second, but since my wavelength is in nanometers, I went ahead and converted this into nanometers. So that's nanometers, there we go, nanometers per second. And I'm going to divide that number by my wavelength, 555 nanometers. And I came up with 5.41 times 10 to the 14th. Now what's my unit here? Well, my unit that I use for frequency is the inverse of seconds, or 1 over seconds. So now I figured out my frequency. Let's figure out what the energy involved is. So now I'm going to use this equation. Energy is Planck's constant. So Planck's constant, which is H, I think it's definitely in your textbook, but if you don't have it written down somewhere, let me just kind of scribble it up here. Planck's constant is 6.63 times 10 to the negative 34th joules seconds. Okay. So let's plug in Planck's constant. 6.63 times 10 to the negative 34th joules per second times our frequency that we just figured out, 5.41 times 10 to the 14th inverse seconds. And so that's going to give me the energy of 3.58 times 10 to the negative 19th joules. Last piece I need to know for this problem, and the energy of a mole of photons of light. So how do we relate this into a mole of photons of light? So what I figured out so far is just the energy of one photon of light, but how do I figure out a mole? Well, let's use our friend Avogadro's number. So if I've got 3.58 times 10 to the negative 19th joules in one photon, how many joules am I going to have in a mole of photons? Well, let's use Avogadro's number. 6.02 times 10 to the 23rd tells me that there are how many photons, there's a period, in a mole. So a mole of photons has the energy of 216,000 joules, or 216 kilojoules. Okay, so you'll see problems like that as you kind of work your way through the text. Does light have mass? Well, we've kind of brought in this idea when we talked about moles, but in a nutshell, no, light does not have mass. But we can look at its energy, and that's where the E is, and look at this lovely equation, E equals mc squared. So you can look at the frequency and the wavelength and relate that. Alright, here's the really important part. When we start looking at the atomic spectrum of the hydrogen model, how does the spectrum work? Well, the cool thing about a spectrum is that it's got two pieces. We've got an emission spectrum and an absorption spectrum. So some light is being absorbed, and that's the black stuff you see. And then some light is being emitted, and this is what we see. And you can tell just as much information about what something is by what's being absorbed than from what you actually see. So this is the spectrum for hydrogen. Down here, this violet color is going to be somewhere in the neighborhood of 410 nanometers. This bluish color is about 434 nanometers. This blue-green is like 486. And all the way over here, this red color is about 656. So we've got all these different bands of light for hydrogen. How does this work? This is where Bohr's model kind of comes in. And the Bohr model of the atom, which you guys have heard of before and it's in your reading, basically what he was kind of saying is that these electrons move in orbits around the nucleus. And these orbits, don't confuse orbits like planetary orbits, not that kind of orbit. These orbits are allowed stable energy states. So Bohr recognized that energy is quantized, that this energy comes out in little packets, in photons. And what his theory is that when these electrons get excited, or something happens to cause these electrons to move from one state to another, that the photons will be emitted or absorbed by electrons only when it changes from one allowed state to another. Okay, so the biggest piece behind the Bohr model is that photons are emitted or absorbed by electrons. So the electrons are the thing that's causing the light, the color, but only when it changes from one allowed state to another. And so those allowed states are the orbits that we're thinking of. Okay, the more energy that you have, so when you get these packets of light, like the 410, so if you see this purple, it kind of looks like it's falling from the 6th level down to the 2nd level. So the farther something falls, the more energy it's falling with. And so then that corresponds to a different light. Remember that these n's, and so if this is the ground state, the n refers to the energy levels. And so we'll kind of go back over electron configurations. But n is one of the quantum numbers. It's the first energy level. So what Bohr was looking at were these electrons changing energy levels, and then photons are either being emitted or absorbed as they do change. So, an electron can bounce up this way, Well, that's where you get the black pieces. That's where you get energy being absorbed. But then as it falls to these different other states, that's where you get the bands of colors. Why is this useful? Well, we can use this kind of thing for a variety of different pieces. We can figure out unknown gases. We can figure out, if you look at the stars and the sun, we can figure out all kinds of what elements go into these things, because each element has a very specific pattern, and here's a few examples there. And we'll take a look at some of these in class with a little bit more practice. But to further kind of go off of what Niels Bohr was doing, he came up with this equation to kind of help explain things mathematically. Z, this is referring to atomic number. N is referring to the level of the electrons. Okay. And remember that E is our energy that's being released. So you might see some types of calculations involving the energy being released. And so we could go ahead and figure out, well, how much energy is required to excite a hydrogen electron from the 1 level to the 2. And then we could also calculate the wavelength of light that might be absorbed by a hydrogen atom in its ground state to reach that. Well, this would be a pretty easy little calculation to do. We're just going to take a look at what is the energy at each level. So let's call that E1 and E2. And because we're talking about absorbing energy, I'm going to make this a positive. Okay, 2.178 times 10 to the negative 18th joules. So that's the energy being absorbed. Times the atomic number, since we're talking about hydrogen, that's 1, so we're going to square 1. E, the first energy level, so let's square that. So this is pretty easy math. So the energy involved with the first energy level is just 2.178 times 10 to the negative 18th. For the second energy level, since we're still absorbing energy, let's calculate how much energy would be at the second energy level. It's still hydrogen, so I'm just going to square 1. But it's the second energy level, so I'm going to square 2. Plug that into my calculator, and I come up with 5.445 times 10 to the negative 19th. To figure out, what the question's really asking me is, what is the change in energy? So how much energy is being absorbed? I'm just going to subtract those two numbers, so I come up with 1.63 times 10 to the negative 18th joules is the amount of energy that have to be absorbed. I could then translate this into figuring out what is the wavelength. Why? By using Planck's constant, okay, or in Planck's calculation. I'm going to have to expand this a little bit since I need to know wavelength. So I'm going to need to put in my wavelength and frequency relationship there. So now we can kind of plug in some numbers. So let's go ahead and solve for our wavelength. So it's going to be Planck's constant, which is h, times the speed of light, which is c, divided by the energy. Planck's constant is 6.626 times 10 to the negative 34th joules seconds. Okay. Times 3.0 times 10 to the 8th meters per second, speed of light, divided by the energy that we just figured out, 1.63 times 10 to the negative 18th joules. I plug that into my calculator, and I come up with 1.22 times 10 to the negative 7th meters, which translates into 122 nanometers. So now you can look back at your electromagnetic spectrum and figure out where does that feature. With these energy calculations, the biggest thing that you really want to pay attention to is the relationship between nanometers and meters. If you don't know that from physics, probably want to jot that down somewhere. Well, the Bohr model worked fantastic for the hydrogen atom, but it falls apart when you start getting into other multi-electron atoms. Why? Because you end up with repulsive forces between electrons. So the problem, then we'll just take helium as an example. So helium, atomic number 2, and it's got 4 protons and neutrons. So imagine here you've got your protons, and they're positively charged. And then you've got these electrons, right? Well, what happens when you bring negatively charged particles together? They repel. So we get these repulsive forces between the electrons, and this is what explains some of the differences in the sublevels. So even within a different sublevel, and by sublevel we're talking about S and P and D and F, and some overlap between the energy levels. Why does 3D have more energy than 4s? It's because of these repulsive forces between the electrons. So the Bohr model gives us a great picture, but it's not quite adequate enough to really explain what's going on. Okay, back up since slide 11 seemed to go black. Quantum mechanics. So now we're getting into the meat. Quantum mechanics is the currently accepted model. There's a lot of different scientists involved: Heisenberg, de Broglie, Schrödinger, and really this is getting at answering the question, where are the electrons in the atom? It's pretty complex when you get into the mathematics of it, because we can't really say for sure where. Not really where the atom is, but where the electrons in the atom are. We can only say where we think it might be. Part of it comes from Heisenberg's uncertainty principle, and Heisenberg's uncertainty principle basically said that you cannot know both the exact position of an electron and its momentum at the same time. You can know one, but you can't know both at the same time, because as soon as you figure out one, the other one is changing. Momentum of an electron. So that was his contribution to quantum mechanics. Schrödinger, all kinds of complicated math to go along with this stuff. So he made an equation from the hydrogen data, so kind of took Bohr's work and created what they call the Schrödinger wave equation. And what he came up with were shapes, not orbits, as Bohr's model have. And these shapes were really probability distributions. So he gave us an area to say, well, the electron is somewhere in this particular area. Now, common misconception, guys, is when you think about Bohr's model and you think about an orbit, do not confuse it with what we're about to talk about, an orbital. Orbitals, these are not the same. Orbitals are the probability regions that Schrödinger described with his calculations. Orbit is how Bohr was thinking in terms of these electrons. So let's take a look at these shapes, and hopefully they're kind of a refresher from last year. These came from, they're basically the square of Schrödinger's wave functions. This is what the s orbital looks like. I think of it as spherical, S for sphere. I don't know if that's real, but it works for me. These are what the p orbitals look like, kind of propeller shaped. A lot of textbooks use dumbbell. No clue where they get that from. I see propeller. The other thing that I want you to kind of see here is notice that when we move into different sublevels, you've got multiple orbitals. So the s sublevel can only have one orbital. It only has one shape. The p sublevel has three shapes. So there's three orbitals, px, py, pz. And so the x, y, z kind of refers to how are they oriented in space. Here's the d sublevel. Notice that there's 5 different shapes. So the d sublevel has 5 different orbitals. And then this is cool. This is the f sublevel. So the f sublevel has 7 different shapes. Now, an orbital, remember from last year, can hold how many electrons? 2! Yes. So you can only have a maximum of 2 electrons in one orbital. So then you can kind of extend that to say, well, how many electrons can fit in the s orbital? And the answer would be 2. And how many electrons can we find in p? 6. How many in d? 10. And how many in f? 14. Hopefully you remember that from last year. Okay, so here's the new stuff. Where are the electrons? How do they feature? The shapes come from mathematical equations, and these equations have variables, and these variables are called quantum numbers. So really, each electron has its own address, and that's what these quantum numbers are doing. The principal quantum number is n, and we saw those last year. Sorry, this table didn't translate very well in PowerPoint for me here. But n is our principal quantum number, and this is, you think of it as like your energy level. And what are our possibilities, and what are our possible examples? Well, n can be anywhere from 1 to 2 to 3 to 4 to 5, 6, 7. Nice. 6, 7. You get the picture. So here's your values for n. The azimuthal quantum number. This is the angular momentum. Its level is L. This is our subshell. So this is S, P, D, and F are the symbols that we typically use for it. But its range of values are going to be, you can kind of see this here, 0, So it's based on what energy level you have, the n. N minus 1, but greater than 0, is where your azimuthal quantum number is going to be. So what if your n equals 3? Say, for instance, you're at the third principal energy level. What are your possible values for L? So n minus 1, well, that's 2. And then L itself, there's 1. And then 0 is your options. What this kind of corresponds to is if you have an L value of 0, you're talking about the S sublevel. If you have an L value of 1, that's your P sublevel. An L value of 2, that's your D sublevel. And an L value of 3, that's your F sublevel. So you can kind of use that to go back and forth. The third quantum number is the magnetic quantum number, projection of the angular momentum, and it's m sub L. And this is when if you've got px, py, pz, what is the particular orbital's location or orientation in space? It's talking about the energy shift. So that's the technical meaning, but it's easier for me to kind of think about how is it oriented in space. Possible values, so positive L to negative L. So for instance, if L equals 2, so remember if L equals 2, you're talking about the D sublevel. What are our values? Well, you go from negative 2 up to positive 2 and all the values in between. Remember that the D sublevel has 5 orbitals to it, so this should kind of make sense why we've got 5 possible numbers here if my L equals 2. The fourth quantum number is spin, the spin projection number, or spin projection quantum number. And so we use little up and down arrows to represent that, but its official symbol is m sub s. It has values of negative 1/2, positive 1/2, so it's going to be either direction. Now let's take a look at how we would use these things. So say, for instance, you were going to do an orbital diagram for oxygen. Okay, so remember these from last year? We had 1s2, 2s2, 2p. Here we go. And so let's fill in all of our electrons for oxygen. So our 2s is full, and then in our 2p we've got 1, 2, 3, and then there's a down arrow right there. So there's our orbital diagram for oxygen. The purpose behind the quantum numbers is to say, okay, I want to know what is the location of this electron right here. What is its address? So how would we go about doing that? Well, first of all, what's the energy level that it's at? Well, it's at n equals 2, right? Because it's 2p. What's its L value? Well, this is the p sublevel, so L has to equal 1. What is the m sub L value? In other words, which orbital is it? So if you look at these, and sometimes I kind of write it underneath, this is going to be negative 1, 0, 1. Because so your m sub L is based on your L. So you go from positive to negative there. So this particular one is negative 1. And then what is its spin? What is my m sub S? What is its spin? Well, I'm looking at the down arrow, so that's going to be a negative 1/2. Let's try another one. Let's just pick some random electron in the middle of the D sublevel. So D has 5 orbitals there. And say it was something where my 3D was completely full. So let's put in all my little arrows. And guys, if you don't remember how to do these orbital diagrams from last year, please make sure you come in and see me or read your book and stuff like that. What do we got? Well, let's label these things. Negative 2, negative 1, 0, positive 1, positive 2. So if I wanted to pick on this particular electron right here, what is the address of this particular electron? I know its n value. It's 3 because we're at the 3D level. I know its L value because I'm at the D sublevel. My L value has to be 2. My m sub L. So which particular one am I at? Well, this is going to be 0. Okay, so the m sub L is which orbital, which orientation in space. M sub S is it the up arrow or the down arrow? This is the up arrow, so my spin is going to be 1/2. Right? All right, well, that's a little bit new from last year. This should be a refresher from last year, the things that influence our electron configurations in the periodic table. So there's three big principles that guide how you complete an electron configuration. The first one is the Aufbau principle. The Aufbau principle says that electrons occupy the orbitals of the lowest possible energy first. Of lowest energy first. Okay. The second one is the Pauli exclusion principle. Orbitals may contain only 2 electrons.
Okay, I'll be silly and ask, why are you still here?
Same energy level. Sorry about that, guys. See, the software gods were sort of working with me this afternoon. Until all orbitals contain 1 electron with the same spin. Okay, so what do these things kind of mean? Electrons occupy orbitals of lowest energy first. So it's got to fill in at n equals 1 first, and then to n2, and then n equals 3, and 4, 5, and so on and so forth. Pauli exclusion principle. Orbitals may contain only 2 electrons, each with opposite spins. So no 2 electrons are going to have the same address. They're all going to have a unique individual address, but one's going to be an up arrow, one's going to be a down arrow. So one's going to be plus 1/2, one's going to be negative 1/2. Hund's rule. Enter each orbital at the same energy level until all orbitals contain 1 electron with the same spin. So if you remember the bus, you know, when you get on the bus, somebody sits in an empty seat, next person gets on a bus, they're going to take the next empty seat until all seats are filled, and then they go back and double up. Remember that the periodic table is kind of read like a book. So when we go through these things, and when I say it's read like a book, that we move right to left and we go top to bottom. So remember energy levels, 1, 2, 3, 4, 5, 6, 7. And then here's your S block, so the S sublevel, the P block over here, D block elements, and then your F block elements. Let's do a couple quick examples just to see how good we are with electron configurations. Cobalt. Let's take a look and see if we can find cobalt. So cobalt is atomic number 27. So what would the electron configuration look like for this? It would look like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d7. So we can count over 7. Let's do one more. Tin. Tin is right here, atomic number 50. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. Now, wow, this was really long and annoying. You remember there's a snazzy little shortcut that we called core configurations, where you took the noble gas that preceded that element. So if I was going to do a core configuration for tin, I look for the noble gas that comes before tin, krypton. I put that in brackets, and so that represents the core. And then whatever's left over, what I'm really looking at are basically the valence electrons, the ones that are on the outer shell. So this is going to save us a ton of time. Now, guys, on the AP test, you will see both. Just pay attention to the question. If it asks you for a full electron configuration, it's looking for this bad boy. If it just says electron configuration, feel free to use the core configuration, use the little shortcut. Now let's wrap this one up by kind of talking about a couple of the exceptions to the rule. We didn't get into these at all. We gave you very basic patterns. But hopefully what you see if you take a look at a periodic table is that there's going to be ones that don't look like your pattern. For instance, chromium. If I did, and let's just use the core configuration for chromium, 4s2, 3d4, this is how you would have written it last year. Well, what's really going on? Well, let's take a look at the orbitals. Okay, so let's draw out the little orbital diagrams. 4s, 1, 2, 3, 4, 5, there's my 3d. And let's fill in my electrons. 3d4. Okay. Well, there's this quirky little rule that basically says that there is a much more stable configuration for this chromium atom than as I have written it. What happens is that this electron actually gets promoted and gets up to the 3D. So really, the core configuration, or the electron configuration for chromium, is 4s1, 3d5. It's more stable this way. This is a more stable configuration. You'll notice the same thing is going to happen with copper. Now last year, if you wrote a core configuration from copper, you would have said argon 4s2, 3d9. But let's take a look at what that orbital diagram might look like. 1, 2, 3, 4, 5. There's 3d. And we got our 2 electrons there. And this is 9, so 1, 2, and 2, and 2, and 2. See, my arrows are getting nice and lazy. Well, what's going to happen with copper is, again, there's a more stable configuration. This one is going to get promoted and fill up the 3D energy level. So really, the electron configuration for copper should be argon 4s1, 3d10. This gets at the idea of stable orbitals. Full orbitals are the most stable. But what you'll see is that half-full orbitals are also stable. So you're going to see all kinds of exceptions to the rule. There's tons of exceptions here. You really don't need to worry about those so much for the AP test. They don't really pick on those too much. But you will see copper and you will see chromium with those exceptions to the rule, and trying to explain why is this a more stable configuration. So you kind of got to look and see, well, is it better to have 2 half-full orbitals or 1 full and 1 half full? And in this case, since there's already 9 in 3D, 1 more electron is going to make that full. So it's better to promote this electron from 4s here. One last little thing, let me throw something out there. 2 pieces of vocabulary that you're going to see in various places throughout your textbook. Squeeze this in wherever you got some space. Are these 2 notions of something being paramagnetic and diamagnetic. Now we will use these to kind of describe properties of different elements. But if something is paramagnetic, you're looking at an atom with 1 or more unpaired electrons. Unpaired electrons. So take a look at those electron configurations, and if something is unpaired, it is considered to be paramagnetic. If it's diamagnetic, all your electrons in the atom are paired. You'll see in later units why these 2 words are important, but for now, just kind of jot them down and make a note of them. Well, guys, that is it. Chapter 6. Have a good day. See you later.